push button?
Yep.
Great.
So I think that works.
1, 2, 3 test. Yes, it's on. Thank you. Yep.
So welcome back, everyone, for session 14 of the conference. And it's my great pleasure to introduce Guido De Marchi, who will tell us about some beautiful near-spec spectroscopy in this gorgeous cluster. So over to you, Guido.
Thank you very much, Chris. Thanks a lot. So indeed, in this talk, I'll be telling you about our study of star formation in NGC 346, the most massive starburst region in the Small Magellanic Cloud. And in this project, that will also be covered in the next talk by Nolan Hebel, we try and constrain the properties of a complex stellar population of multiple generations and try to understand the physical parameters of the stars, including the very important mass accretion rates, but in an environment which is very similar to the environment that you could expect at high redshift in the early universe. NGC 346 has been studied extensively in the past, also with Hubble. With my collaborators, for instance, we searched for pre-main sequence stars by looking for objects with H-alpha excess emission in their photometry, because this is a very good indicator that the stars are actively accreting. And we developed a very solid method that combines broadband photometry in the V and I band with narrowband H-alpha imaging, and that allows us to identify hundreds of pre-main sequence stars that are actively accreting with a strong H-alpha excess emission at the level of 5 sigma or more that corresponds to equivalent width of more than 20 angstrom in H-alpha. An important thing is that from the derived luminosity of the H-alpha emission line, we can characterize the accretion luminosity and the mass accretion rate. And we have applied this method to a number of star-forming regions, and the bottom line is that in the Magellanic Clouds in general, and in NGC 346 on the right in particular, pre-main sequence stars appear to accrete more and for a longer time than in nearby star-forming regions around the Sun, like the small star-forming regions, Taurus, Orion, Ophiuchi, etc. And you do find, in the end, we find a lot of pre-main sequence stars that are still accreting when they are very close to the main sequence down here, which means that they have to be, older objects. And there is a clear trend, because in the Magellanic Clouds at low metallicity, stars appear to accrete more and for a longer time, probably because of the lower radiation pressure of the central star on low metallicity disk material. So the star is less efficient at blowing away the disk stays there for a longer time, and the accretion process continues. And this produces very large mass accretion rates. We find objects that are 20 million years old, several of them, 20, 30 million years old, that are still accreting at a rate of 10 to the minus 8 solar masses per year, which is 2 orders of magnitude larger than what you have in nearby star-forming regions around the Sun for objects of similar age and mass. So I do understand that in the community there was some skepticism about these results, because it's all based on photometry, and we are telling you that in the Magellanic Clouds at low metallicity, the situation is completely different from the one that we have around the Sun. So why is that? Well, luckily, with JWST and NIRSPEC, we can now dispel those doubts. we have used the NIRSPEC microshutter array to study 20 pre-main sequence stars in NGC 346, this beautiful region, stars that we had identified with Hubble with ages between 1 and 30 million years, and lo and behold, the spectroscopy show all of them are still accreting. Please, what I'm going to show you is still under review, so do not take pictures, do not tweet, or do not, well, it's called X now, right? Don't X about it now. Please, if there is interest, if there are members of the media in the room, or if there is interest later on, I'll be more than happy to talk, but we have to respect the embargo. So JWST and NIRSPEC in particular has this fantastic microshutter array, which is an array of 250,000 little doors as thin as a human hair that you can open and close at will. So what we do is we point the telescope, make sure that the stars that we want to study are at the center of a microshutter, shut up everything else, and this will project a beautiful spectrum of all the sources on the detector. If I zoom in, you see the fantastic emission lines. Some of those are due to the nebula, some of those are due to the stars. Look at these pairs, for instance. On the left, you always have the helium-1 line, which is purely nebular. On the right, you have Passion Alpha, which is due to the nebula, but also can be contributed by the stars themselves when they are accreting. Now, in NGC 346, the background is highly variable, so it has to be removed. And to remove the background, what we do is we take a spectrum in a neighboring microshutter, and we subtract it from that of the star, as Kieran showed us yesterday. And to properly rescale and subtract the background, we use as a reference those emission lines that are only due to the nebula, the helium-1 line that I showed you before. And this works beautifully. Now, I'm going to show you 3 spectra after background subtraction as an example. A very young pre-main sequence candidate that had been determined, as pre-main sequence candidate with photometry, 0.1 million year old, 100,000 years old. An older pre-main sequence candidate, 25 million years old, and a much older star, a main sequence star about 1 giga-year old. Those objects can be compared directly to one another. They have the same mass, 1.2 solar masses, the same value of extinction. AV is only 0.5 here. It's not, not very extinguished region. So, and these objects we had determined, derived, identified with our H-alpha access method that told us the first 2 are actually actively accreting because there is H-alpha access emission in the photometry. The third one is not. So what do the spectra show? Well, the one on top clearly is a very young star. A very, very young star. Look at those beautiful, prominent recombination lines, Passion Alpha, Passion Beta, bracket Gamma, bracket Delta, bracket Epsilon, you name them, right? Most of these are seen for the first time because they're not accessible from the ground. The main sequence star, you see absolutely no emission at the wavelengths of the recombination lines of hydrogen. So this tells you that, yes, it's a main sequence star, but more importantly, that the background subtraction works. And what about a 25 million year old star? Is it accreting? Oh, yes, definitely. You clearly see these emission lines, and it's not as strong as those for the very young stars, as you would imagine, but it is accreting. So this is clearly a confirmation that there are stars 25 million years old that are still accreting. But the most important thing is that now we have those wonderful emission lines from which we can derive the accretion luminosity and the mass accretion rate much more accurately. And the accretion luminosity for those stars derived from the Passion and the bracket series agrees to better than a factor of 2 with the values that we had estimated from the H-alpha photometry taken 18 years before. A factor of 2, 18 years. Now, if you know something about pre-main sequence stars, you probably know that they vary a lot in their accretion luminosity, easily by a factor of 2 over periods of days and weeks. So this tells us that Hubble had done a very good job. But much more importantly, it tells us now that we can measure directly from the spectroscopy the mass accretion rate, and we do find that those stars are accreting at 20, stars at 20, 30 million years old, they are accreting at a rate of 10 to the minus 8 solar masses per year. Fantastic. So this is the first important result from NIRSPEC, which is in this low metallicity environment. This is a massive cluster in the Small Magellanic Cloud, but also think about the early universe. In this environment, stars accrete at a higher rate for a longer time. So it takes longer to form a star like the Sun in this environment. And we know that those stars are still surrounded by a circumstellar disk because we also see the near-infrared excess in the spectra caused by the dust in the disk. The dust that is warmed up by the star, and it shines back in the infrared. In our own galaxy at solar metallicity, after, say, 5–10 million years, you no longer see the near-infrared X's because the dust has disappeared, the disk has been dissipated, planets have formed, so there is no more dust there. But here, the situation is very different. So what do we see here? Here we see the continuum underlying the spectra of 7 pre-main sequence stars. You see the ages indicated on the right there in different colors. And at the bottom, you see here a dashed line, which is the continuum underlying a typical main sequence star in this field. Again, those stars can be compared directly. 1.2 solar masses, 0.5 AV is the extinction, and they have temperatures between 5,000 and 8,000 Kelvin. They are all registered at the same value at 1.7 microns, so you can better see the difference in the spectral energy distribution. Now, let's start from the main sequence star, the dashed line. I'm comparing it here with these beige and greenish thin lines, which are theoretical models for main sequence stars in the small Magellanic Cloud with the right metallicity, or temperatures between 5,000 and 8,000 Kelvin. And all of them fit equally well the observations, which is what you expect, because here we are in the tail of the black body distribution, so the temperature doesn't actually affect the shape of the spectrum. However, in the same range, our pre-main sequence stars have much more flux. And this is the flux that is caused by the near-infrared X's, by the dust in the disks. And we know not only that around those stars, the spectra of those stars contain indication that there is near-infrared X's because of the dust, that contain prominent recombination lines because the atomic hydrogen which is being accreted, but we also see for the first time fantastic and very strong molecular hydrogen excitation lines. Now, molecular hydrogen is much denser and colder gas that can be excited because of shock or because of extreme ultraviolet radiation due to other stars. And here, the ratio of intensity of those lines, many of those lines were shown yesterday in beautiful talks. The ratios tell us very clearly that here the environment is fully consistent with gas at a temperature of 2500 Kelvin, which is shocked because of, simply excited because of shock. So this is what you expect in a circumstellar disk because of outflows, but you normally have this around 1 or 2 million year old stars, not around objects that are 25 million years old, such as this one. So again, it's an indication that the formation process takes longer here. And we can, and this is my last slide, we can actually pinpoint exactly from where that excited molecular hydrogen is coming. It is on the right, you see a cartoon of the microshutter, which if you want is a long slit, 0.2 arcsecond wide and 0.5 arcsecond tall, long, and it's divided in 7 rows that correspond to the 7 pixel rows that the spectrum is projected on the detector. And the star in this case is between row 2 and 3, and the symbol there gives you an idea of the size of the PSF of NIRSPEC. Now, if you look here on the left at the spectra of the 7 individual spectra before background subtraction, look at this one, the helium-1 line, which is a nebular line. You see it's pretty constant along the entire microshutter. And also the bracket gamma line is present at all locations along the shutter, but it is stronger at the position of the star itself. Why? Because it is a nebular line, but the star is accreting. So it's contributing its own part to the bracket gamma line. But look now at the molecular hydrogen excitation line. Here, you see it's only and exclusively at the location of the star. There is nothing above, and there is nothing below. And because molecular hydrogen cannot be in the star, it has to be in a filament, in a cocoon, in a disk associated with the star. And actually, with the resolution that we have, we can set an upper limit to the size of this disk of approximately 6,000 AU, which, within a factor of a few, is consistent with the values that we find in our galaxy. Of course, this is just an upper limit. It's probably much smaller, but we have this indication. So my time is completely up. Let me come to the final summary. With NIRSPEC, we have demonstrated that in this low metallicity environment, this is a massive cluster, but also think in the small Magellanic Cloud, but think about the early universe. Stars accrete more and for a longer time, so it takes longer to form stars. For the first time, we see prominent excitation lines of molecular hydrogen around objects that are 20, 30 million years old. And the fact that around the same stars, we see near-infrared X's means that there is disks, there is dust, and so think about planets. In these environments, planets have more time to form and to grow than they have in nearby star-forming regions as solar metallicity. So how was it in the early universe to form planets? I don't know. Thank you very much for your attention. I'm ready for your questions. Thank you.
Thank you, Guido. Fantastic. So we have Naomi being our virtual moderator again. I hope out there. Are you out there, Naomi?
Yes,
Great.
I am.
Have we got any questions
I have
online?
a question.
Right. I'll
Yes.
let you go first.
From Thanawuthana Sabodi, I have, for the 25 mega-year-old star, how do you distinguish the HI emission coming from accretion versus chromospheric activity?
Oh, thank you so much. Yeah, indeed. Corona activity is important for objects that are of that age. The point is that corona activity would have to have the H-alpha excess emission, or much better, the Paschen alpha emission that we see in those stars. Let me see if I can. Paschen alpha emission that we can see here is orders of magnitude larger than what you'd expect because of basically due to activity of the star. So it is really an order of magnitude larger. So that's why we have equivalent widths of order 200, 300 for those objects, and that is not what you expect for due to activity of the star. So that's how we do that.
In the room, and then I think there's one more online, and then we'll move on. So if we can do.
Yeah, Laura Flagg, great talk. So for the H2, first of all, it can be in the stars because it can be in the star spots, and this has tortured me, so now it gets to torture you. But also, can you use, I don't know, the velocity resolution to also help constrain where the H2 is coming from?
Unfortunately, our velocity resolution, particularly with these observations, is not good enough. But we're going to get a second epoch, and we're going to get a different region in the Large Magellanic Cloud where we have higher resolution. So for that, we will be able to say something about the velocity.
Awesome, thank you.
Thank you.
Really beautiful work. This is Elizabeth Tarantino at Space Telescope, and I have a question generally about the interpretation. So NGC 346 is like a supergiant H2 region with like 40 different O stars. So how can you be sure that this that the impact of the accretion is due to the metallicity and not because it's a very energetic environment filled with a bunch of different O stars? And how come you interpret it to be due to metallicity and not the overall environment?
Okay, excellent question. This is a higher mass region than the typical torus or lupus, where it is very low mass. So clearly there is a component due to the mass, and that we already saw when we compared the H-alpha excess emission with the photometry. So now we understand that we can properly read what we had done. Yes, clearly this is a much more massive region. But if we compare this region with 30 Dorados, which is somewhat lower metallicity and a very massive one, or with the objects that Kieran showed yesterday, NGC 3603, very massive, but at solar metallicity, we clearly see an additional effect. So there is clearly a component due to the density of the region, but a more important component is coming from the metallicity. At least this is what Hubble told us with H-alpha excess emission, and we seem to be able to confirm it now with the spectroscopy. Thank you.
One more online, Naomi, is there?
Yes, I'm not sure if this has been answered, but Colin Norman asks, physically, why does the low metal environment accrete for longer?
Whether it's known, well, look, I think, Colin, we probably have discussed about this in the past, but I think the idea is that it could very well be that the radiation pressure of the star, as I said, is less strong on low metallicity, this material. The amount of light is the same, but in order for the radiation pressure to work, you need to have metals in the disk, and iron in particular. And if you do not have enough iron, probably the same radiation pressure doesn't make the same effect. So that is, but it's an idea. So we should discuss Colin about this, because there might be some very nice theoretical interpretation that can be made. Thank you.
Great. So thanks, Guido.
Thank you very much.
Guido again.
Thank you.
So, heard about pre-main sequence stars in 346. Now we're on to young stellar objects with Nolan Howell. So.
All right, thank you. And thank you to Guido for that great introduction. So let's talk a little bit more about NGC 346, and in particular, some of the young stellar objects that we're finding in this region. So let me reiterate the idea of cosmic noon to start off. And so that's the idea that star formation in the universe peaked very early, and peaking at around a Z of 2 to 3. And again, that's the time when metallicity was significantly lower. And so the questions that we have when we're looking into NGC 346, considering the metallicity, are does this cause formation to occur on different timescales for planets and stars? Guido talked a lot about that already. And with this lower metallicity, is there even dust present for planets to begin forming? And what I'm going to argue in this talk is that these are problems that require resolving individual stars. And of course, if you're interested in star formation at the peak of the early universe, that's very difficult because it's very difficult, if not impossible, to resolve any individual stars. And just for a little more background on YSOs, if you're actually able to look at the individual star formation going on. So YSOs go through a process where at the beginning they're enshrouded in lots of gas and dust in a very dense envelope. And as they evolve, that envelope is either blown away or accreted onto the star, ending up with a pre-main sequence star that has just a disk around it. And all of these stages in evolution come with a characteristic spectral energy distribution. So you can see that going down from the top here. You start off with an SED that has a peak over in the longer wavelengths, and just on this, because this is in frequency space, this is over on the left. And as you evolve into a class 1, class 2, and class 3 pre-main sequence star, that peak in the SED shifts over more into the visible wavelengths, into shorter wavelengths. So where NGC 346 comes into this is there's a great proxy for the early universe. So just again, to introduce it again, it's a prominent young cluster located in the Small Magellanic Cloud. It's around 62 kiloparsecs away. It's one of the brightest and largest star-forming regions in the Small Magellanic Cloud. And again, we can use this as a local laboratory to investigate low metallicity star formation on the individual level. So one thing that I kind of want to impress is that JWST is to NGC 346 what Spitzer is to the Milky Way. So to say that another way, with JWST's resolution that's comparable to HST, but now in the infrared, JWST can actually enable star formation studies like the type done in the Milky Way with Spitzer, but now out into extragalactic environments. And so previous studies of NGC 346 with Spitzer had found around 100 YSOs, but they're all massive YSOs, so with masses around 8 solar masses or larger. And JWST now can actually reach down over 10 magnitudes below Spitzer and 2 magnitudes below HST at comparable wavelengths. And I think I've always liked this comparison, but so you see at the top here, an image from Spitzer from the exact same region. This is just a Spitzer image that's blown up. And now with a comparable wavelength in JWST, you can see that this, which was identified as a cluster of YSOs, now can really be resolved, and you can see just so many different sources there and so much different star formation going on. So to look at all of this, in our program, our GTO program, we have coverage with NIRCam and Miri. In NIRCam, we have 6 different filters that gives a broad coverage over much of the near-IR SED. And as well, we have a medium and a narrow filter, and the medium filter, the 3.3 micron filter, gives us coverage over PA features, which are important for identifying dust. And the 1.8 micron feature covers the hydrogen passion alpha recombination line that yesterday we heard a lot about. Similarly, in Miri, we have 5 filters that give, again, coverage over the mid-IR SED. And 2 of those filters in particular cover PA features, the 7.7 and 1.1 micron filters. And as well, we have the 10 micron filter, and that's actually very important for detecting silicate absorption, which is in protostellar envelopes. And I just wanted to show the footprint that we have of these observations. So again, this is just the field in Spitzer. And then in NIRCam, you can see we have coverage over this entire area, and similarly in Miri. So for much of this region, we actually have coverage in the near infrared all the way into the mid infrared. So with NIRCam, if you've seen this image before, when we look, we can see all kinds of complex structure from energized hydrogen, molecular hydrogen, dust. And in particular, in comparison to the Spitzer images I've been showing, you can see a lot of individual stars. So you can actually distinguish individual stars and YSOs. And this means that you can actually do photometric analysis of individual sources. But if I zoom in even more, you'll notice NGC346 is a really crowded area with a very complex background. That means you need a really good photometry tool for it. And so I wanted to plug Starbug2, which is a photometry tool created specifically for these challenges by Connor Nally. He's here with us. He has a poster. I encourage you to check it out. So Starbug2 is written in Python. It uses a whole ensemble of methods to do background subtraction. And as we can see on the right, this is just a comparison between Starbug and the James Webb Pipeline, which can also do photometry. But Starbug can outperform the James Webb Pipeline by an order of magnitude, detecting far more sources and at magnitudes far lower. And so using this, we can do aperture photometry and PSF photometry. We have PSF photometry now with all of our NIRCam data, and for Miri, we use aperture photometry. At the moment, we're waiting for the PSF modeling to catch up. This is just another example of how great Starbug is. So on the left, you have an input image and one of the backgrounds that's generated, and so it can just basically just make all those stars disappear, which is very important for when you want to do PSF photometry. Okay, so looking at NIRCam, just with NIRCam, we could detect almost 20,000 unique sources across all of the widebands, and in common with in all the widebands, almost 25,000 total sources. And already in doing this, we could find candidate pre-main sequence stars with the 115 filter that extended to 2 magnitudes below HST detections, so from previous work. And that's already suggesting that we can observe YSOs down to around 0.1 solar masses. And in particular, we can do more analysis of the individual SEDs to pull out different populations, or CMDs, I should say. So this is one example. So we can identify a branch of more evolved sources here, a split off into the red giant branch. We have the red clump. But most importantly, we can find a lot of YSOs and identify those, in particular, many that have this Paschen alpha excess, indicating that there's ongoing accretion. And if we look even particularly into another longer wavelength, we can tell that we're detecting a lot of these young sources with this IR excess. So that's indicative of dust. In total, we have around 500 of these sources. And that's actually a bit of a conservative estimate because these are actually going to be going into a future follow-up near-spec program. And now I just wanted to show Miri. This is a great image that was made by Katja Ferran. I believe there will be a press release coming out in August that has a nice new picture of this. So this has not been published yet at the moment, so if you want to hold off for that press release. So again, with Miri, we can also see this diffuse, even colder gas structure traced out. And in particular, what you notice when you compare the NIRCam and the Miri images is that the star cluster that was in the background here just kind of melts away when you get into the mid-infrared wavelengths, and the younger, more deeply embedded objects start to shine more brightly. So we can also do analysis of CMDs with Miri. And very interestingly, we see this sort of track of evolved stars sitting at 0 and this population of younger YSO candidates. And in essentially all of the Miri CMDs, we could find these two populations just separating out. And that made it easy to define a color cut in each of the 10 possible CMDs with Miri for identifying young candidate sources. So anything here that's marked with a red X. And notice that some of these are already overlapping with YSOs that have been identified with NearCam. So in total, there were 1,001, just luckily, sources that we identified with Miri that are possible YSOs. And if you just tally how many times in the CMDs they pass that red color cut, you can sort of group them. And you notice here where I've grouped those that pass more with red and purple, those actually fall more along all of these filaments than do the ones that are passing just a few tests. You'll notice those are more dispersed. So that's telling us that we're actually seeing star formation in these filaments. So this is going to talk about a little bit some upcoming work. But so we have this coverage over all of these wavelengths in NearCam and Miri, 11 filters. And with that, we can start doing some SED modeling. So this is some work that has taken 43 of some of the best Miri-identified YSOs, taken their photometry, and run them through SED fitting from Robotile 2017. And in doing this, we can start getting parameters like the radius, the temperature, the luminosity, and the mass. And so here's just a distribution of the masses that we have at the moment. But I fully expect, well, I guess let me say, so at the moment, we already are having masses that are down to 1.5 solar masses when we're doing this fitting. And I fully expect that we're going to be going even lower. And so we'll be able to get model-fitted SEDs of objects with lower masses. And we'll also be having specifically some follow-up observations with Miri MRS. This is the SED that's been fitted for one of the targets. This should be conducted, I think, anytime. But yeah, so with Miri MRS, we'll have coverage over all the channels and wavelengths. And I just wanted to go briefly and talk about what we can expect when we actually get this data. So I encourage you to look for Ishinayek's poster here. So this is an example of not data from NGC 346, but data from a region N79, which is in the Large Magellanic Cloud. But this was a similar program that got Miri MRS spectroscopy. And so what we saw with this was that Miri MRS was very good at disentangling YSO clusters and finding multiple sources in what was previously seen as just one object with Spitzer. And already the spectra is showing features from dust, from gas, and from ice. So in gas, there is already molecular hydrogen, again, indicative of possible outflows and shocks. There's atomic hydrogen recombination, indicative of accretion. Lots of PAW features, many lines, and some of them can also give indications of accretion and accretion rates. And in particular, many ICEs, which are present in the very youngest, most embedded YSOs. And so let me go just to my summary then. So yeah, to summarize, James Webb is reaching at 10 magnitudes below Spitzer, and 2 magnitudes below HST at similar wavelengths. Already we're finding YSOs that are down to 0.1 solar mass. For the first time in an extragalactic environment, we're detecting embedded low mass star formation. We have YSOs with near-infrared excess from dust. Again, this indicates that there's a possible reservoir of dust for rocky planet formation at low metallicity. And we detect around 500 YSOs and pre-made sequence stars with NearCam alone, and a potential 1,000 other YSO candidates with Miri. And from these, we can get model-fitted SEDs, determine protocell parameters like radius, temperature, luminosity, and mass. And all of this is going to inform future follow-up studies with Miri MRS. Thank you.
Thanks, Nolan. It's great to see the Miri image in there as well. Any questions online, Naomi?
No, nothing online.
Okay. Any in the room? Nicole.
Hi, Nicole Arulanantham, STSCI. I have a question about the distribution of stars that you were able to identify with Starbug. It looked like it was bimodal. Is that significant? And if so, do you have a sense of what that really faint population might be?
Let me see. So this was the plot, I think. I don't think it was bimodal. I think this is probably a starbug test that was run on a region that actually had a bimodal distribution, not because it was detected with starbug as a feature of starbug being, detecting in a bimodal way, but because I think there, if this is NGC346, there's a cluster in the background that is not associated with it, which has separate characteristics. Oh, okay, there you go. Yeah, red clump and a giant branch.
Hi there, Josh Peltonen from the University of Alberta. I was just curious how your catalog of YSOs compares to the ones that we're seeing in Spitzer, if you identify all of their YSOs or if they're split into multiple, or how does it look?
Yeah, there are a number of sources that are split into, well, they're distinguished as multiple sources with James Webb. So that was one of the things that was an issue or a concern when looking for follow-up targets for the MRS. So many of the previous bright sources in Spitzer, again, we found were actually multiple sources. And many of the very brightest sources in Spitzer actually ended up saturating, even at the relatively shallow depth that we had. So most of the sources that you get, yeah, most things in Spitzer that were identified as YSOs are those massive YSOs. Yeah.
We'll have to move on then, sorry. So if we can thank Nolan again. Moving forward. Thank you. Cameron Mullen, who will move into direct imaging of YSOs now. And is your mic on?
I believe so, yeah.
Cool.
All right, thank you so much for this opportunity to present my research. I'm a master's student from the University of Victoria, working with my supervisor, Dr. Rubing Dong. And today I'm going to be presenting the work we've done with direct imaging of 5 protoplanetary disks. So this is all part of a NIRCam GTO program led by Dr. Jaren Lesenring from the University of Arizona. We have several team members who I've listed here. Gabriele and Jaren are both also at this conference, so if you have questions about this work, you can also direct them to them. But today I'm going to be representing the team and presenting the work we've all been doing over the past year. So our program targets 5 protoplanetary disks. For those of you who may not be as familiar, a protoplanetary disk is just a region of dust and gas surrounding a young star. And so our 5 targets are shown here, and what you might immediately notice is that they all have pretty distinct morphological characteristics. So MWC758 and HD135P44b both have these 2 large spiral arms. And then HL Tau and TW Hydra both have multiple rings and gaps, and PDS70 has large cavities. And so, of course, one of the questions would be, what is creating these features? Well, if you run a simulation and you inject a multi-Jupiter mass planet about 100 AU separation from the star, you can create very similar spiral arms to what we're seeing with the real MWC758 data. And similarly, if you take a disk and inject multiple Saturn mass planets at these different separations, then they'll carve out gaps in the dust and gas and create these ring features that we're seeing with HL Tau. And so clearly one of the leading theories is that these characteristics, these features that we see, are the result of interactions between planets and their host disks. And so our goal with this program was to view these 5 targets and then see if we can detect and characterize forming planets within them. In the case of PDS70, there's already been 2 confirmed protoplanet detections before, PDS70b and c, and our goal with that disk would really be to redetect those planets and see what else we can see. For all 5 of these disks, there are going to be publications, each led by the relatively junior members of the team, whose names I've listed below each of their respective disks. And some of this work, I should say, is still in progress, so I would ask that you not share any of the images I show today outside of the conference. So for all of the disks I'm going to be sharing with you, we took our data in direct imaging mode. So we didn't use the chronograph, somewhat to our disadvantage, as it would turn out, but I can get to that a bit later. But this is all direct imaging. We utilized 4 different wavelength filters, 2 narrow ones for accretion, and then 2 other filters for continuum emission. And we used, for each filter, 2 telescope roll angles to allow for a technique known as ADI, angular differential imaging. And at each angle, we took 4 dithers. So I'm going to start with the disk I'm the most familiar with, and that is HL tau. So the image you see here is obviously not a NIRCam image. This is from the ALMA 2014 long baseline campaign, where there was the famous multiple rings and gaps shown in this disk. And of course, this is an image taken at millimeter wavelengths, and our question would be, how does our infrared James Webb data add to this picture? All right, so what I'm showing here is I've taken the ALMA data in red, and I've overlaid our NIRCam data at 2 microns in blue. And you might be wondering what exactly we're looking at. Well, this is mainly a lot of scattered light from the envelope. So HL tau is actually a relatively young star. It's estimated at around 100,000 years old, which means that for those of you in star formation, you might be familiar that young stars like this are often embedded in stellar envelopes, and HL tau is no exception to this. So we're mainly seeing the envelope. We also have this C-shaped outflow, which has been previously imaged at other wavelengths, but we also detect it here with this higher level of detail with NIRCam. Now, if you have a sharp eye, you might also notice the 8-pointing speckle pattern from the NIRCam PSF in sort of the southwest corner. So this is actually raw data. The PSF has not been subtracted here. It's not maybe immediately obvious because the envelope dominates so much, even in our raw data, but this is actually raw. So the question would be, what do our reductions look like? So here I'm showing the reductions in all 4 wavelength filters, and the key features, so the top 2 panels go out to 2 arc seconds, and the bottom 2 go out to 4. And what we're mainly seeing is a lot of envelope scattered light, which is visible in all 4 wavelength filters. We also, in our 2 longest filters, detect part of an inflowing gas spiral. This was previously imaged in the form of HCO plus emission with ALMA, but we detect it here as well in the infrared. Now, if you're wondering where the disk is, the disk would be here. Well, this is the location of it. We don't, unfortunately, actually pick up the disk in any of our wavelength filters. And this just comes down to the fact that the disk goes out to about 1 arc second, which in our data where we suffered from a lot of oversaturation is both a saturated region and one where we're dealing with oversubtraction. So we don't unfortunately detect the disk. We also, disappointingly, don't see any convincing point source candidates for this source. But with our detection limits, we should be sensitive to planets as small as 1 Jupiter mass out to 4 arc seconds. And in the disk region, we'd be sensitive to multi-Jupiter mass planets. All right, so the next disk I'm going to be discussing is MWT 758. You can see our reductions along the top here. This is one of our spiral disks. And what I'm showing here is some simulations that were done before we received our data, where we're trying to predict sort of what we'd be able to see. Obviously, we were predicting the 2 spiral arms, and then we have these 2 point sources, multi-Jupiter mass planets, which have been injected and circled in red at the approximate locations that we might expect to see planets if they're driving the formation of the spiral arms. And so if you do this combination of these 2 wavelength filters, we actually do resolve the spiral arms quite nicely. So it matches sort of previous observations, but we don't unfortunately detect any convincing protoplanet candidates. Now, if you have been following this disk at all recently, you may have seen the Wagner et al. 2023 Nature publication, which did claim a protoplanet candidate detection in this disk using LBTI. So an obvious question would be, why don't we detect it here? Well, the simplest answer is probably that it just comes down to sensitivity limits. So the LBTI detection was done in the L prime band, which in wavelength is most similar to our 4 micron filters. So if you look at this sensitivity plot here, at the angular separation of this point source, in this wavelength, in direct imaging mode, LBTI is somewhat more sensitive than NIRCam. So unfortunately, this point was probably just too far below our detection limits. However, we did suffer from a lot of saturation with this disk, and so there is going to be a follow-up program done in cycle 2 with a coronagraph, and hopefully we'll be able to reach deeper limits and redetect this planet candidate. If we do, it will be somewhere around here. So the next disk I'm going to be discussing is a similar one, as it's also a spiral disk. This is HG135344b, also known as SAO. In this disk, we do resolve the spiral arms partially in 3 of our 4 filters. In F410M, we don't see the spirals, but more excitingly, we do see a point source candidate. So what you're looking at here, this candidate we've labeled CC1, and it has some characteristic features for what you'd expect for a planet candidate when you're using the ADI technique. So it has the bright inner center and then the 2 negative side lobes. And these are the exact sort of characteristics, these exact sort of features that you're looking for if you're trying to spot planets. But we aren't making any big claims. CC1 does come with some grains of salt. So as I'd mentioned earlier, we do only detect it in 1 of our 4 wavelength filters. And there is also the matter of where we detect it. So if I show here, again, in green, this is the simulations that were done before we received our data. This is where the spirals are located, and we've circled approximately where we'd expect planets to be if they are driving the formation of the spiral arms. And clearly, CC1 is about an arcsecond further separated. So considering its mass and considering how far away it is, if it is in fact a bound companion, it is very unlikely to be driving the formation of the spiral arms. So CC1 could be a real planet, but it doesn't explain the spirals. Those still have not had companions detected closer in. Also, just quickly, some sensitivity limits. The green point shows our sensitivity at the location of CC1, and we do see it falls slightly below the green curve, so we don't detect it with full 5 sigma confidence. But if you have more questions on this particular source, Gabriele is really the expert here. He has mass limits and accretion rates and whatnot on his posters, so you can direct them to him. The last disk we have received data on, as of right now, is PDS-70. So here I'm showing our reductions in 3 of our filters. These are all very, very preliminary. We only received this data really recently, but we do see the disk, and we see what look like point sources and what could be the locations of planet B and C. So that's really exciting, but this is all really new, so we can't make any confirmed claims yet that we're definitely seeing these planets, but these results do look very promising. And we're interested, of course, in seeing where this data will evolve in the next few months as we get to work on it more. So lastly, just to sort of wrap things up, obviously I've only talked about 4 disks, and there are 5. We haven't received our data yet for TW Hydra. We'll be getting that by the end of December. And as I mentioned, we'd had some saturation issues with our other disks, but luckily with TW Hydra, we were able to request a coronagraph. And so hopefully with that disk, we'll be able to reach deeper sensitivity limits and not be suffering with the same oversaturation issues. And we're excited to see how that data will look. So there's still some work to be done in this program, and you can expect to see a lot more coming out of this in the next few months. So with that, I'm just going to leave our publication statuses here, and I'll be happy to take any questions you might have.
Thank you. All right. So thank you. Naomi, are there any online questions?
No, nothing yet.
Okay. All right. I can imagine there's several people in the audience who want to see the TW Hydra data. So I'll go to John first, and then another couple of questions.
So John Deb with Space Telescope. Just to clarify, did you take any reference star images as part of the program?
Right, so we don't have any reference stars. It's unfortunate. It would have been helpful with HL Tau specifically, but yeah, we didn't take any reference stars. Yeah.
Hi, Laura Flagg. For PDS-70, do the potential point sources have similar properties to what's already been detected in the infrared for the companions?
Right, so like I said, we only got our PDS-70 data super recently, so we've just done like very quick reductions. We haven't really done any sensitivity analyses or anything else on those specific points, but stay tuned for the work that we're going to be doing. Yeah.
Looking forward to it.
Hi. You seem a bit disappointed with the final results, but I think they're really, really nice. I think you should be really happy with them. I am curious about the spiral arms that you see in Passion Alpha filter. Is that brightness purely coming from the fact there's an overdensity, or do you have any thoughts on the mechanism producing it? Because we're relying on Passion Alpha to be an accretion tracer, and so this could confuse the picture.
Right, that's a good question. Yeah, I think that might be a better question for some of my colleagues. I haven't worked as closely with the spiral disks, so in terms of the actual mechanisms creating the arms, I don't think I can give a very satisfying answer.
No worries, no worries.
Good question, yes.
Okay, thank you, thank you.
I know there's another couple of questions, but if we can thank Cameron again. And mic'd up. So we go from spectroscopy to 1001 to 5 to 1 target. And Marshall Perrin will tell us a bit about the debris disk of beta pic. Right.
Looks right. All right, very good. Thank you all. So Marshall Perrin here from Space Telescope, and before I get started talking about beta pic, I want to highlight the early career researchers who've really been leading this work, names in bold at the bottom. Isa Rebolledo, Jens Kammerer, both who had been postdocs here at the Institute and have now moved on to next positions, and Kellen Lawson, who's at Goddard. So I'll be talking about NIRCam and Miri, high contrast imaging of beta pictoris, and really focusing in on the fact that we're seeing the aftermath of a massive collision in the disk. So beta pictoris, of course, is the first debris disk system that was ever spatially resolved, angularly resolved, and seen after detection of the infrared excess from IRAS, then seen with this image on one of the ground-based early stellar coronagraph, and of course followed up extensively over so many studies over really the last 40 years. This is kind of a cornerstone of the study of circumstellar disks. And on the bottom, I'm showing some recent results, showing both AO images of the disk, the 2 planets that we now know are within it, at least 2 planets, imaged, spatially resolved, and the exquisite orbit precision, dynamical constraints on this system possible with VLT gravity. Within the disk, within the structure of the disk, we've been able to see over the last years both the nearly almost exactly edge-on plane of the disk itself and this inclined inner disk. Let's see which button is the laser. There we go. This is Hubble ACS images. There's a fainter secondary component here, seen with ACS, with STIS, with NICMOS. And there's also observations from the ground, CO that shows there's a clump of gas. There's gas on this side, and asymmetries within the disk that have been interpreted as a sign of a collision in this area, and then asymmetries, perturbations of the disk resulting from that. There's a series of programs studying beta pic with basically every high contrast capability that JWST has. The NIRCam and Miri coronagraphy, I'll be talking about the results from a telescope GTO program, but I would also want to highlight that there is a separate Miri GTO program that's using other wavelengths. This data was just taken a week and a half ago, so not yet analyzed, but stay tuned for more wavelength coverage. Miri MRS spectroscopy. See the very next talk, Caden Wortham will be presenting those results. There's also aperture masking interferometry and NIRSpec IFU reflectance spectroscopy of the disk. So this is a combination of GTO and GEO programs studying the system. Now, in beta pic, as I was just saying, has been studied by every possible telescope from ground to space for the last 40 years. So of course we're going to do it with JWST, but I was really wondering before we got the data, is it really going to surprise us or not? Or we're just going to fill in the blanks of things we've already knew on this disk. So wind back the clock with me to December last year. The data is coming in, and from our team Slack, you know, as our Christmas present, sort of a year after launch, the data shows up, and of course, in the masked preview images, you can see the disk. I'm so used to in high contrast imaging the kind of work that Cameron was just talking about, where you're digging in to see really faint signals and trying to pull out things that take effort. Well, in this case, I get the raw data from MAST, nothing's calibrated. What's that, right? What's going on down here? There's this thing that we've never seen before that's not detected at any shorter wavelengths, and it's visible in the raw data with JWST. 20 minutes from file hits the MAST to new discovery, possible because of the 20 years of work that went into putting this observatory up there. So yes, we did reduce the data after that to get these images with both NIRCam and Miri. This is going to be in a paper by Isa Rabiito in PrEP, showing here the different wavelengths of the NIRCam data and the two Miri filters we have. Then Kellen Lawson has taken this and done a deconvolution. This is a chronographic deconvolution handling the PSF spatial variations. And you can see here, even just by eye, sort of the warp of the disk, a little brighter on these sides, and the NIRCam data, and really zooming in on the Miri data, this extended feature coming off of the disk to this outside. There's a lot of other details. I'll come back and show this image zoomed in more detail in a second. We, of course, do see the planet, the known planet Beta Pic B is detected in all the NIRCam filters. We don't see it in Miri, in our wavelength Miri. The disk is brighter at 15 and 23, but again, stay tuned for the next talk. And the photometry is seen for B really is very consistent with the results extrapolated from the ground, placing a consistent picture of this as a young Jovian atmosphere around 1700 Kelvin. We do look for, but do not find, fainter lower mass planets down to about a 0.1 Jupiter mass detection limit in the outer regions of the disk. And I will say Beta Pic C, of course, is within the inner working angle of the chronograph, is not seen in these data. So going back to this beautiful Miri image, where you can see that the main disk plane is rotated horizontal in this image, and two main sort of additional features. On so this is the southern side. We call this the cat's tail coming up. The disk has a tail, and on the other side we have a fork. There's really two mid planes, two lines extending out from here. I'll go to back, take the if I can take that off, so you can kind of see here. There's a brightness extended there. And this has been seen before. Look in particular the beautiful HST STIS work done by Daniel Apai and team. But I also want to draw your attention to this part of the field where there's this extended clumpy nebulosity up here. And your first thought is, well, this is just an imperfect PSF subtraction. But no, this is astrophysical. This is real. And we can demonstrate that if we look at the two individual rolls of the coronagraph. And so if we roll the whole observatory, all this systematics change, but these features stay fixed in the sky frame. You can also see the same stuff at 15 microns, at 23 microns, through different portions of Miri, independent observations. So this is all real clumpy fluff. Something has really been a puzzle for us to understand what this is in its relationship. And I want to say again, the STIS observations show a fan of diffuse material in this quadrant as well. So it's consistent with that from STIS. So we've developed a dynamical picture, the hypothesis that we think explains what might be going on. And I should credit Chris Stark for this work. So you produce dust in a system, and that dust may stay on a bound orbit, may move out of the system, really dominated by the radiation pressure on the dust. We have this factor beta, the ratio of the radiation pressure to the force of gravity. And so depending on how that is, it will be bound or not. And so in this case, you produce dust here at the point of a massive collision. Some particles, the ones that stay bound, but they'll be launched into these eccentric orbits that make a large fan here. And the unbound particles will spray out in a path away from the debris point, departing the system. You then rotate that to an edge-on, or not quite edge-on inclination. This is a planar system here, but you get this extended and then this sort of angled up part just from line-of-sight inclination effects in this model. And so we think that this can tell the story of what we're seeing here. This image shows after subtracting off the main disk, this extended feature out here, and then the cat's tail coming up. This is the bound dust on those eccentric elliptical orbits. This is the pieces blowing out of the system. In the model, you can produce something that looks like this tail if most of the dust is all clumped around a single value of beta. You're producing preferentially dust that all is being blown out under radiation pressure in the same way. Is it plausible that all the dust that's produced from this collisional debris has that same ratio of beta? It turns out, yes, we think that is possible. This is work, Jessica Arnold, who was previously at Carnegie DTM, modeling the more complicated agglomerates and porous dust, and found that in this case, specifically for beta PIC, modeling different dust compositions, it happens to be that highly porous, very porous dust particles, and I would look here, Carolyn Gray talked of these as dust bunnies, right? These very loose, extended, mostly vacuum particles. And it turns out that almost independent of dust grain radius, most of these highly porous particles have a beta value that is indeed around, it's a little bit above 0.5. So it's in the right ballpark if this highly porous silicates is most of what's coming out of the collision. There's certainly details that are not explained in this. I mean, going back again to that clumpy fluff of nebulosity, that might be other pieces of dust that are coming off. So we have a large portion of the dust that's going off in this one tail, and other pieces of debris. It's not truly a single stream. There's other stuff going off here to fill in that fan. So again, to summarize, the Miri imaging shows us this view of structures that have been there all along, but we have never seen before at shorter wavelengths. The cat's tail and the fan we have seen at shorter wavelengths. And we think, again, there's the hypothesis I just described, but I think there's details still to be worked out. But we're seeing, this is a hit and run of some massive planetesimal collision within these two belts in beta PIC. Of course, as well as studying the planets through the NIRCam coronagraphy. So 2 papers coming out soon from our team. Isa Rebiito on the disk, Jens Kammerer on the planet. Thank you. Happy to take questions for the AFRA team.
Thanks, Marshall. Great stuff. Naomi, anything online? That's a no.
No, nothing yet.
Are you allowed to ask one?
Hi, Jaron Lysenring, University of Arizona. So I was wondering, with the porous silicates, can you get spatially resolved spectra with LRS or MRS or anything to try to see if it's actually...
Stand by for the next talk. Good setup.
That was not planned. You missed that last time.
Naman Bajaj, University of Arizona. I was just wondering, could this be very small dust grains entrained in the gas, and the gas is the one leaving the system?
Say that again, please.
Could these be a very small dust grains entrained in the gas, and the gas is actually leaving the system?
So, I don't know that we have. I think the gas velocity is a good question. I thought the gas was in roughly Keplerian, not departing the system at high velocity, but I could be mistaken on that. I'm not there. I'll have to look at that for the gas velocities. But I think we would expect a range of dust particles, some of which would be small enough to be entrained in the gas, many of which, though, would be unbound. There was one in the middle, too, was one of the sort of first hands up.
Someone else who hasn't asked a question yet?
Hi, Joel Green, Space Telescope. So is it, I mean, maybe it's really obvious, but it's not possible that that's infalling as opposed to exiting? I guess would there be an accretion shock or something if it was infalling?
Yeah, I don't think we have evidence. That's a good question. Infalling dust that's not seen, you would not expect the infalling dust to mostly be larger particles as opposed to smaller. Why you would not see that at shorter wavelengths? If it was like a
very diffuse bit of the cloud that was still coming in late.
I don't think there's sufficient extended nebulosity around this to be substantially accreting at that amount. But yeah, we like lots of hypotheses to explain this because we scratched our heads for a while.
Mark Wyatt from Cambridge. Why is the cat's tail not seen at shorter wavelengths? Does that tell us
really
something
good
about
question. Yeah, it has to say something about either the distance is far enough that it's not sufficiently illuminated below detection sensitivities, or that preferentially, of course, Miri is sensitive to larger particles, right? So if you're seeing thermal emission rather from larger particles, but there's just not enough surface area in the smaller particles to scatter light. But yeah, we've definitely, there's work to be done in some kind of population synthesis to fit that has to explain why we see it in some wavelengths and others. We've looked back to the JWST data and it's not there.
That's great. Thanks for all the questions. Can we thank Marshall again?
I have one question online
Sorry.
that just came through.
Do you want
Is
to
there time?
Go for that, Naomi, while we're getting set up.
Yeah, so Carl Staplefelt asked, why does the major collision produce so much dust out of plane? This seems unlikely.
So we actually don't think that it is out of plane of the truly out of plane. It's partly just it's close to, but not quite 90 degrees, right? So you can get a vertical component that is in the plane of the thing that's inclined 87, 86 degrees to the line of sight, and it's extending up as projected on the sky, even though we think it's not actually, as dramatically out of plane as it looks.
Thanks again, Marshall. And so next up, we have Kadim Worthen, who will now be telling us about the Miri MRS observations of beta Pic as well.
Hello, everyone. My name is Caden Worthen. I am a graduate student at Johns Hopkins University, and today I'll be talking to you about our Miri MRS observations of the beta Pic system. So you just heard from the last talk that beta Pic is host to this very famous edge-on debris disk. And so this illustration or artist representation of a debris disk is shown on this slide, where you have these minor bodies like asteroids or comets that are essentially colliding and grinding down to produce these smaller dust particles, which is what we actually observe. So in some debris disks, we actually see time variability in their infrared excess, indicating that there's some sort of stochastic collision going on human timescales. But you could also have a scenario where you're in more of a steady state process of collisions, where the dust is mostly constant throughout time. So at this debris disk stage of planetary evolution, you've essentially already formed all of your giant planets. So an open question is, does the dust in the debris disk actually affect the giant planets in the system? So we think that planets can affect the actual structure of the dust by inducing warps or gaps in the disk, but we're still uncertain how the disk can influence the planet. Now, in our own solar system, we have an example of a minor body influencing the atmosphere of Jupiter, and that's with the Shoemaker-Levy 9 impact that happened back in the 90s. I'm showing an HST image here on the right, where each of these brown points is a spot where the fragment of the comet actually hit Jupiter. And this was really interesting because it delivered volatile and refractory material to its atmosphere, and we see decades-long impact based off of this, the impact of the comet. So we try to answer the question, is dust, and how much, accreted from disks onto giant planets? So we observed the beta Pictoris system with the Miri MRS, which gets a spectrum from 5 to 30 microns. And so here is just the illustration of the beta Pic system with the scattered light image of the debris disk, and then the two known planets. They're both super Jupiter mass planets. So we observe it with the Miri MRS, which is an integral field unit. So essentially what that means is our final data product is this 3D data cube, where we have 2 spectral dimensions and 1 spatial dimension, or 1 wavelength dimension. So we can do spatially resolved spectroscopy. Now, the way that we observe this is we first observe beta Pic, and then we followed up with a PSF reference star. So we could do PSF subtraction on the IFU data and look for both the planet B and any spatial extended emission. So just to give you a little hint of what the data looks like, here is an image slice at 8 microns after PSF subtraction with the red cross representing the position of the star, and you see this really nice spatially resolved edge-on debris disk. So Spitzer observed beta Pic back in 2004 to get a mid-infrared spectrum, and that's what I'm showing here on the right. And so here the photosphere of the star has been removed, so what you're seeing is purely emission from the dust in the disk. Now, Spitzer detected amorphous silicates at 10 microns and crystalline silicates at 18 microns, indicated by these bumps. So crystalline silicates are essentially grains that have long-ordered atomic structure, and amorphous silicates, the structure is more random. So again, if we observe this with JWST, are we going to see something similar? Are we going to see something different? We didn't know. So let's see what JWST saw. The black is the Miri MRS spectrum of beta pic 20 years after the Spitzer data. And you can see that there are actually dramatic differences. One of them being that the 18 micron silicate feature is gone. 20 years of observations, it's disappeared. So the obvious question, well, where did it go? From the modeling of this 18 micron feature with Spitzer, we know that the dust grains are in the Rayleigh limit. So that means 2 pi a, where a is their grain radius, is much less than lambda. And we know that dust and debris disks is, especially the small grains, is subject to radiation forces and can get blown out. So the blowout size is determined by this parameter beta, which is essentially the ratio of the radiation pressure to the gravitational force on the grain. So if the dust particle has a beta of value greater than 0.5, it'll get blown out onto these hyperbolic or unbound orbits. And if you have a beta value less than 0.5, you can remain bound. So if we make some assumptions about where the dust was that caused the 18 micron feature with Spitzer, and we can calculate a beta based on assuming a size and the composition, we can try to calculate how far these dust grains could have been blown out in the 20 years since the observations happened. And you essentially find that the dust grains can get blown out upwards of 80 AU. And so that puts this either at the edge or past the edge of our MRS observations, and it also puts them at a distance where they'd be cool enough that they wouldn't be emitting significant radiation at 18 microns. So we think we can explain this disappearance of the 18 micron feature by these radiative blowout grains. Now, we can also look at the 10 micron silicate feature, and here we actually have 3 epochs to compare to. We have one from the ground with Subaru Comics taken in 2003, we have Spitzer in 2004, and then Miri MRS in 2023. And we see changes in this feature as well. Notice in the comic spectrum, there's 2 peaks, and they're very sharp. Going a year later to Subaru, you still see these kind of peaks, but the sharpness has already decreased. And by the time we get to Miri in 2023, we have this more broad silicate feature, and we lose this kind of sharp peak. So we're still in the process of doing the detailed dust modeling to understand what is causing this change. But qualitatively, we can come up with a few explanations. One is the removal of crystalline grains. So crystalline grains can produce these kind of peaky features here, seen at 10 microns. And the other is the removal of small amorphous grains. So smaller silicate grains essentially have more narrow features, whereas larger silicate grains will produce a broader 10 micron feature, more trapezoidal shaped, which we see more similar to the Miri MRS. So we're still in the process of figuring out what is the answer to this. But this is essentially super interesting because what we're finding is that the dust is not being continuously replenished in the system. So maybe some event happened closer to 2023, producing this population of grains that essentially get radiatively driven outwards over time, and they're gone by the time we observe them with JWST. So I'd also like to zoom in on that spectrum of the point source to this 5 to 7 micron region, because we see an infrared excess here. And we can fit this infrared excess with a black body shown by this red curve here to figure out what the temperature of the dust is. And you essentially get a best fit dust temperature of about 500 Kelvin, which puts it at a minimum black body distance of about 1 AU. So this is indicating that there's dust being produced in the inner few AU of this system. Now, we also did PSF subtraction, and we can look for spatially resolved dust at 5 microns as well. So what I'm showing here on the left is a binned PSF subtracted image slice at 5 microns. And the purple line here shows the 5 sigma contour, and you can see that we're clearly detecting spatially extended dust emission with JWST at 5 microns. And this black line here shows the aperture for the Miri MRS extraction, and then the red line shows essentially the angular resolution of Spitzer at this wavelength. So this would have been completely spatially unresolved to Spitzer, but now with the bigger mirror, we're spatially resolving this dust with JWST for the first time. Now, it's interesting how you can get this hot dust at long separations, because if you essentially assume that the dust is black body grains, so large grains, you can calculate how hot they should be as a function of distance from the star, shown by this black dashed line here. And essentially from 10 to 20 AU, where we see the dust, you get a black body temperature of about 150, 100 Kelvin, which puts their peak black body emission at about 20 microns. And so they would not be significantly emitting at 10 to 15 AU at 5 microns. But in the small grain limit, you can see that between 20 and 10 AU, you can actually get to temperatures of 350 to 400 Kelvin, where you could emit significantly at 5 microns. So we think this excess, spatially extended excess, is best explained by small submicron dust grains. Now, we have evidence that there's dust being produced in the inner few AU of the system, and we have evidence for maybe this radiative-driven wind outwards of small grains. So if you have that scenario, you have two giant planets at 10 AU, beta Pic B, and beta Pic C at 3 AU. So it's possible that as these dust grains are getting driven outwards, they're impacting the planet and getting accreted onto the planet. And so we want to estimate, what is the dust accretion rate onto these two planets from the disk? So here I'm showing this beta parameter again for two different compositions of silicate grains as a function of particle radius. So the black dashed line here shows a beta of 0.5. So everything above that black dashed line will get blown out of the system. Everything below will remain in orbit. So if we make some assumptions about the particle size distribution and the azimuthal symmetry of the dust, we can estimate a dust accretion rate onto these two planets. And we get something that's very small, 10 to the minus 12 and 10 to the minus 10 order of magnitude lunar masses per year for beta Pic B and beta Pic C respectively. Now, these planets are super Jupiter mass planets, so this is a tiny, tiny fraction of the total overall mass of the planet. So it might not be contributing to the final mass of the planet, but you can imagine that if these silicate grains can remain aloft in the atmospheres of these young planets, maybe they can affect the observed spectra of the planets. Now, in our PSF subtracted cubes, we can search for the planet. And we get a nice detection of beta Pic B. So I'm showing here the image slices across channel 1, so 5 to about 6.5 microns, and we see a clear point source detection at the exact predicted orbital location of beta Pic B based on the ground-based orbit fits. And so this is really exciting because we can get a mid-infrared spectrum of the planet for the first time and search for any sort of, say, dust features. Now, unfortunately, the reason I'm only showing it out to 6.5 microns is because past this wavelength, you can already start to see the thermal emission from the disk is starting to pick up. But at longer wavelengths, the disk becomes bright, the PSF becomes larger, it becomes a lot harder to recover the planet, and so this is our essential cutoff. But it's super cool because here we're using the Miri MRS with PSF subtraction, and we get a 5 sigma detection of beta Pic, which is about 1,000 times fainter than its host star at a separation of half an arc second without a coronagraph. So that is super nice result. Now we can extract the spectrum of beta Pic B from those image cubes that I just showed you. And so the black points here are that extracted spectrum of beta Pic B, and then blue here indicates the best fit atmosphere model to the spectrum plus ground-based photometry and spectral points. So you can see that there's this dip here around 6.6 to 6.5 microns. And that's actually from water absorption in the atmosphere of the planet. So our spectrum here is consistent with this water absorption in the atmosphere. And we don't find evidence for any sort of dust excess. Like, we're able to fit this spectrum with a bare atmosphere. So I can leave up my conclusions then and take questions.
Thanks, Karen. Just quick check. Naomi, any online?
No, nothing yet.
Right. So, Ryan.
Yeah, thanks for the nice talk. So I have a question about the disappearing crystalline silicate feature. So can you get some kind of measurement of like the amount of dust that needs to have been evacuated from the disk, and then can you put a constraint on like the mass outflow and see if that's consistent with what you'd expect?
Yeah, so that's interesting because the best fit to the silicate feature from Spitzer, it puts the dust mass for the 18 micron silicate feature on the order of maybe a lunar mass or so. So it's essentially, and I should say that there's maybe a tiny bump at 18 microns, so we might not have removed all of the grains, but we seem to have removed most of the small grains there. So essentially you're removing maybe on the order of, or a little bit smaller of a lunar mass in the 20 years that you back out. But I also think the time variability aspect is that might not be constant over time. Like, there may be periods of higher activity and periods of lower activity, and we're just catching it at different times by observing it over a 20-year time period.
I have a question online. From Carl Stapelfeld, could the spatially resolved hot dust just be reflected light?
So that's the great thing about having an IFU is you can take a spectrum and see that it has a thermal emission spectrum and is not consistent with like a stellar spectrum or something from scattered light. So we do think it's thermal emission.
So I'm still trying to formulate this question, but you're wondering if the dust is being possibly blown away, and it's going to be better at blowing away smaller grains than bigger grains. And it makes me think of one way that you could investigate that is by seeing if the extinction is changing, because with smaller grains you'll have very strongly wavelength dependent extinction, and when the grains are larger it'll be more gray, and because you're spatially resolved you might be able to actually see if it becomes more gray as you move away, and that would indicate that there are larger grains further away, or the other way around. But if you look, because they did this for a supernova, just as it went off, you have very big grains and they get smaller and smaller, and you can see the extinction law change over time. But you could maybe do that spatially rather than over time.
Well, that's an interesting idea. Are you saying, so extinction changing in visible wavelengths? Or?
Well, if you have recombination lines in your MRS spectra, you could just use line ratios, compare them to case B recombination.
No, we don't have any lines in our spectrum. It's pretty.
That's going to be a problem. Okay. Yep. Too bad. Sorry.
On that note, can we take Cadden again? Go on.
I have one online, sorry. So Will Rocha says, nice talk. Why do you think there's a water absorption feature at 6.5 microns?
Oh, yeah, so I should have showed this a little better, but this atmosphere model here includes water absorption, and if you essentially chop out the water, you essentially get a line that kind of goes like this, and so you miss kind of all of these data points here. Oh, I realize you can't see the laser pointer online, but essentially it's a black body, so you don't capture the data points that follow this kind of peak and dip here, if it's just a pure Rayleigh-Jeans tail of a black body without water absorption.
Cool. Can we thank Cadden again then? Now we're moving to Will, who, if you're there and you can share your screen. Some of the results from Will Rocha from Leiden. Right.
Yes. I'm trying to share my screen.
Yeah, if you put it into display or full screen, or that,
right.
That works as well.
But can you guys see? I just see like some options, but I don't see my screen actually. Okay, I think I.
Got it.
So can you see the slides now?
Yeah, we can see your slides. So.
Okay.
Great.
Is a presentation mode?
Yes, looks good.
Okay, perfect. Right, so thank you very much. So my name is Will Rocha. I am a postdoc in the Leiden Observatory. And first I want to thank the organizers for allowing me to show my results today. I think there's a very nice opportunity to talk about the James Webb data. It's very exciting, work with that. So the title of my talk is Ions and Complex Molecules in Interstellar Ices, Insights from James Webb Observations of Young Protostars, the JWST program. Okay, so inside these dense and cold regions of molecular clouds, some atoms can stick on the surface of very tiny grains, and this leads to the formation of some molecules, and eventually in some conditions, some ions can also be formed. But if you have enough carbon monoxide, the hydrogenation of this carbon monoxide can also lead to the formation of methanol. That was one of the simplistic complex organic molecules that we have securely identified in the interstellar medium. So the point is, laboratory experiments strongly support that not only methanol, but also all the complex molecules, including acetaldehyde, ethanol, and methylformate, can also be formed in this environment. So when the molecular cloud then collapses and the star formation begins, there is an increase of the temperature in the inner part. And because of this increase of the temperature, these molecules dissolve from the ice, they go to the gas phase, and they are rotationally excited. And because of this, they become observable with millimeter and centimeter telescope. And here I'm just showing you one example of this field survey, ALMA spectrum, with different emission lines associated with complex molecules. And the big picture we want to address is how we connect these molecules that are formed in this very early stage to all the stages, including the protostars, the protoplanetary disks, comets, and eventually in evolved planets. So the answers, we want answers with James Webb, for example, how far the chemistry evolves in ices in these regions, and also how these complex molecules are inherited in later stages. So there is actually an apparent paradox of this font, because if you look in the gas phase, as I said, you already see confirmation of these molecules, including acetaldehyde, methylbromate, ethanol, so they are securely detected. But in the ice phase, where we expect that the molecules are formed, basically what we have is only tentative detection. And these tentative detections are based on a transition of this molecule when compared to some observations. And here I'm just showing one example of W33A, that's a high mass protostar. And you see some absorption features that are related with infrared spectra of complex molecules. And you see there is some match between the observations and the laboratory data. So based on this, we have some tentative detections of this molecule. So now we want to address actually this apparent paradox using new observations of protostars with James Webb. And in particular, I'm talking about the JWST plus collaboration. So the JWST stands for James Webb Observations of Young Protostars. The PI is Evina Van Stuk and Mike Hessler. And there is a list of other members of this team, and perhaps some of them are attending the conference in person, so you can talk to them as well. So JWST has many different sources and is composed by GTO and GEO programs. We have around 30 sources. We have Miri and NewSpec data for some of them, and this is EU and the US collaboration. So the first source is a high mass protostar, IRIS 23385. We have different images of this region. And the last one is the Miri MRS in 6 microns. And actually, we can resolve the source, and we see that there are 2 objects in this region. So that's also interesting from the spatial resolution from the Miri data. And the second source is IRIS 2A, that we see one source, and also we can see some structure probably related to some outflow in this region. So these are the Miri MRS spectra of these 2 sources. We see multiple absorptive features, including ices and silicates. And the region actually that I want to focus in my talk today is this one highlighted by the cyan color. So here is where we expect to see fingerprints of complex organic molecules, specifically oxygen-bearing complex molecules. And we are going to address this region today and show what we have done so far. So again, this is a work in progress. And I expect that you don't show this data in social media in particular. But yeah, let's see what we have done so far. Before we go for the ice specifically, we have to do a few other steps before. So we have to isolate the absorption features using a global continuum. And basically here we use the global subtraction by a polynomial method. So it's a 3rd order polynomial. And this basically means that we have some emission, dust emission, but we don't distinguish the region that's emitting with the simplistic method. But when we subtract the continuum, the next step we have to subtract the silicate feature. And here we combine olivine and pyroxene to do the subtraction. So these steps are basically for IRIS 2A that I'm showing here. So when we subtract then the silicate, we see the subtracted spectrum. And the region that we are looking at is this one inside the blue region. So you see there is a small feature here. This is actually real. It's an SO2 gas emission that actually you had to remove it to do the ice analysis in this region. And this was done by one of the postdocs in our group. Martijn van Helder. So after this, all steps of subtraction, we have to do one more. That's actually you have to remove the contribution of water that's present in this region, and also NH4 plus that's super strong in this spectral region as well. So then we use it a third order polynomial subtraction, and when we do that, we review actually the isotopes of features in this range. And this method has been used multiple times in the literature, and it starts like, for example, in 1999 by Stewart. So then, as I said, we have this clear isotopes of features in this range. And now we start doing the spectral decomposition using the Enigma fitting tool. So this is a code I developed myself when I was a postdoc in Copenhagen, along with my collaborators there as well. So Enigma stands for decomposition of infrared ice speakers using genetic modeling algorithm. And this is based on a genetic algorithm optimization. We have several infrared spectra, a large laboratory database to do the fit, and also have a robust statistical analysis afterwards. So in a nutshell, Enigma gives you the spectral decomposition, you can calculate column densities, and you can do statistical analysis like that. All right, so let me now start with the spectral decomposition of Iris-2A, the low mass delta star. So in black we have the distribution, and in green we have the Enigma fit. So now let me guide you through each component contributing to this fit. So the first one is CH4. We expected to be here already from previous observations with ISO and also Spitzer. And we see like how much CH4 is contributing to this range. So we saw actually the first surprise that's actually OCN minus. That's an ion contributing to this blue wing of this band. And SO2 was already tentatively detected in the past. So actually basically have these three molecules contributing to this strong band. And another thing was HCO minus, that's the formate ion that has similar intensities and contributes to this band at 7.2 and 7.4 microns. And now we have the first complex organic molecule that's ethanol. So ethanol in the past was assigned to the 7.2 micron band, but here in this range we see that ethanol has actually three strong bands contributing to this fit. Now going to the right side, we see formic acid that's present around 8.2 microns and is very broad, and we also expect to see this molecule from the 6 micron band. So the second complex organic molecule we identified was methylformate. So basically we have this green spectrum showing the features of methylformate, and the other one is acetic acid contributing to the 7.4 micron band. And finally, to get some excess around 7.8 microns, we saw acetic acid. So this is a list of the molecules that we found using the Enigma fit tool to perform this spectral decomposition. So we repeated the same procedure now for a high mass protostar. This will have a lower signal to noise ratio. So I'm not showing all the steps, but the only thing different that we did not find here was that we did not we did not see the features of acetic acid in this source in particular. But all the other molecules are assigned here as well. So we also did some statistical analysis because we want to be confident about the robustness of this detection. So we did confidence interval analysis, and in particular, I want to focus only on ethanol. That's actually, you see like the strongest band in this lower part of the spectrum, the blue, in the yellow color. So in this plot, I'm showing a chi-square map. So we have different components, and we correlate all together in order to see if you have a 3-signal confidence interval robustness of the fit. So I want to just to pay attention on this small part that have ethanol. And what we see is that ethanol, the 3-signal confidence interval, never gets to 0, which means that you cannot exclude ethanol as a component of the fit. We repeated for acetaldehyde, and we have the same thing. So acetaldehyde, ethanol are robust detections based on this analysis, and we repeated the same for methylformate, and we could not exclude it, methylformate as a solution. Talking a little bit about ethanol, so we also did another analysis changing the temperature of the infrared spectrum. What we could see is that between 15 Kelvin and 100 Kelvin, we cannot distinguish any difference in the ice. So all are possible, but then this will change, start changing if you go above 100 Kelvin. Not only that, but we also considered other solutions, other complex molecules, and basically what happens is that these other components, they get very low recurrence, which means that they are not, we are just assigning them as a tentative detection in our feed. So acetaldehyde, ethanol, and methylformate are also robust based on these recurrence analysis. Some implications, some ice gas implications is that we calculated column densities, and we did, for example, the ethanol acetaldehyde ratio, and we saw that in the ice they are above 1. So when we look at for the gas phase ratios as well, they are always above 1 too. So perhaps what's happening is that we have some ethanol formation based starting from acetaldehyde, and if this is starting in the ice and then dissolve to the gas phase, basically what we're saying is that they are formed in the ice and they basically dissolve to the gas phase. So this suggests like a solid phase formation for this molecule. We also compared with gas cometary abundances, and here is different histograms showing different abundances compared to water ice. So in black we have histograms for comets, and in red we have for protostars, and we see that these molecules are depleted in the comet. Similar conclusions we got in our work. So basically, we get similar depletion in the comet by a factor of 10 or 100 for different molecules. Also, we did compare to methanol, ice. So this actually is a gas phase correlation plot showing a protostar and the comet 67P, and they found a good correlation with a factor of 10. So our work shows a good correlation as well with the effect of 5. So we got actually perhaps is indicating that we have close inheritance from protostallite phase. So to conclude, these are my take-home messages. So we have analysis of James Webb observations that indicate that these cones are present or even formed in the ices, including ethanol, acetaldehyde, methylformate, and acetic acid. So our analysis also indicates that these cones are inherited at late stage. And finally, I think that this first year of James Webb is improving our knowledge about astrochemical origins, and this, of course, will guide us to a thrilling odyssey in the next years as the frontiers of ice research are expanded. So thank you very much for your attention.
Thanks. Thank you, Will, for joining us. So a quick virtual check-in on any questions online.
Nope, nothing yet.
And any in the room? I think I saw something pop up on Slack. I don't know if that was... Will, someone asked on Slack about the Enigma fitting. Does the fit also give the temperature of the molecule?
Yes, we also have a recurrence plot for different temperatures. So what happens is that we cannot distinguish the temperature of the ice, usually below 80 Kelvin, 80 Kelvin. We cannot distinguish any difference of this ice. So the difference starts happening when you have above 80 Kelvin.
Great, thank you. And there's at least one in the room here.
Joel Green, Space Telescope. I just wanted to ask, just as a follow-up, so with these particular detections and potentially inheritance, does that suggest anything about the formation pathways for the planets and disks, or is it too early to say anything about which specific things got inherited and whether that affects things?
Mm-hmm. Yeah, I don't think that you can really say anything based on this analysis. For planet formation itself, we can say actually that we see some different features. For example, for methylformate, we see that the spectral feature in the high mass stars is different of the low mass stars. So this perhaps is indicating that you have a different mechanism or chemical pathway to form this molecule. But I don't think we can extend this to planet formation yet.
Thanks, Will. Any final takers in the room or online? If not, propose we wrap for lunch and come back here at 1:30. And can we thank Will and all our speakers again from the session? Thank you.
Thank you.